Welcome to question 9, the final question on the second spec paper release, paper 1. Citric acid is a weak acid. Explain what is meant by a weak acid. Well, if we turn to the unit 4 chemical changes, OH minus H plus, the acid reactions bit, we can see this bit here, strong and weak acids, higher tier content. Okay, a strong acid completely ionizes. It completely ionizes to produce H plus and negative ions, and it's the H plus ions that cause acidity. So all of the molecules of HCl in this instance, they all ionize, they all split apart to form H plus and Cl minus. So every 1 mole of HCl produces 1 mole of H plus ions, and that's what causes acidity. A weak acid, on the other hand, well, here's an example here. This is ethanoic acid. Only some of the ethanoic acid ionizes to form H plus ions and a negative ion. So I've got a lot of the unionized molecule and a small amount of the H plus and the negative ion. So in answer to our question here, what's meant by weak acid? Well, it's something that creates H plus ions, but it's not fully ionized. It doesn't create as many H plus ions as it theoretically could. It's a difficult question. A student titrated citric acid with sodium hydroxide solution. This is the method used. Pipette 25.0 cm cubed of sodium hydroxide into a conical flask. Add a few drops of thymol blue indicated to the sodium hydroxide solution. Thymol blue is blue in alkali and yellow in acid. Add citric acid solution from a burette until the end point was reached. Explain what would happen at the end point of this titration. Refer to the acid, the alkali and the indicator in your answer for 3 marks. Right, what we're doing in the titration is we're taking a fixed volume of an alkali, right, in the flask, and we're seeing how much acid we need to exactly neutralize it. So at the end point, that's when we're getting the exact neutralization. At the end point, for our first mark, the indicator is going to change colour. Okay, that's what happens at the end point. It's the exact moment, the exact point that the indicator changes colour. In this instance, okay, the colour change we're going to get, well, it's blue in alkali, and the alkali is in the flask where we've added the indicator. So we're going to start blue, and at the end point, it's going to be at the very point it turns yellow. So for our second mark, it's where blue turns to yellow. Our final mark is to say, at the end point of a titration, I've got exactly the same amount of alkali as acid. Or to put it another way, the alkali has been exactly neutralized by the acid. Explain why a pipette is used to measure the sodium hydroxide solution, but a burette is used to measure the citric acid solution. Right, so the sodium hydroxide solution, for the sodium hydroxide, we're adding a fixed volume, 25.0 cm cubed. Okay, so a volumetric pipette is a good way of measuring out a fixed volume of something. So fixed volume is a pipette. But we're looking to see how much acid exactly neutralizes that, and we don't know. That's what we're trying to find out. So I need a way of adding an exact variable volume. And a burette, this tube here with a marking down the side and the tap, I can add it, I can turn the tap on and add it until the end point, then turn the tap off, and it is added an exact variable amount. I've measured how much I've added. So a burette, a variable volume is how we use a burette to add a variable volume. Table 4 shows the students' results, and you can see I've already messed this up once, so this is the second run through with this. Students' results, we've got 5 results. The equation for reaction is this, which we'll come on to in a minute. The concentration of sodium hydroxide was 0.102. Concordant results are those within 0.10 cm cubed of each other. Calculate the concentration of the citric acid in moles per dm cubed. Use only the concordant results from table 5 in your calculation. You must show you're working. Of course you must. Right, so First of all, concordant results. Well, concordant results mean that they're similar enough. They're similar enough to form a mean. And we've been told that our tolerance here is 0.10 cm cubed. So our results that we're going to form our mean with need to be within 0.10 cm cubed of each other. So let's look at them. We've got 12.15 and 12.15. Well, they're clearly within, they're the same. So they're clearly within 0.10 cm cubed. So if I'm going to use those two as my starting point, I need anything that's maximum 12.25 or 12.05. That's 11, so that's no good. 12.10, yeah, that's close enough. That's within 0.05, so that's a concordant result, so that can go over there. 13.5, that's well out. So I've got three results that I can use to form my mean. Here I am forming my mean, 12.15 plus 12.15 plus 12.10. So that's 36.40 divided by 3 gives me 12.13. So that is the amount of acid, that's cm cubed of acid added. Now I need to calculate the concentration of the citric acid in moles per dm cubed. Well, let's put this for my formula. Citric acid plus NaOH gives whatever, we're not interested, right? We're just interested in adding how much of this exactly reacts with that. We can see the reacting ratio from our equation up here. The reacting ratio is 1 to 3. That means for every 1 mole of citric acid I need 3 moles of NaOH. I'm told that I've got a volume. I've got a volume of sodium hydroxide. The volume of sodium hydroxide was 25 cm cubed. 25 cm cubed. I've got a concentration. The concentration of sodium hydroxide is 0.102. If I've got a volume and I've got a concentration, I can work out moles. Right? So I could work out the moles here. What am I being asked to calculate? Well, I'm being asked to calculate the concentration of citric acid. So I'm after this box here. What other pieces of information have I got? Well, I know the volume of citric acid. Well, I worked that out, didn't I? The volume of citric acid was 12.13 cm cubed. I don't have a moles, so I can't yet work out the conc. But if I worked out the moles of sodium hydroxide and I know the reacting ratio, I can go from there to there, and from there I can go to there. So if we look at our mind map for Quant Chem, it's this one here. It's the moles, conc, vol formula triangle. Yeah. Moles, conc, vol. Right. But I've got to remember my volume has got to be in dm cubed, and my concentration has got to be in moles per dm cubed. Otherwise it won't work. What have I got here? Well, I've got a concentration in 0.12 moles per dm cubed, so that's good. But this volume is in cm cubed, so I need to convert it to dm cubed. And the easiest way to do that is to divide it by 1000. So I've got a volume now in dm cubed, it's 25 divided by 1000. I've got a concentration, that means I can work out the moles. So 25, turn it on, 25 divided by 1000 equals times 0.102 equals, my moles is 0.00, no significant figures yet, first significant figure, second significant figure, third significant figure. That's the moles of NaOH that are present in the conical flask. I can now take this moles number and work out this moles number. The reacting ratio is 3 to 1. So every 1 mole of citric acid needed 3 moles of NaOH. So to convert this moles number, I times by this one and then divide by this. 0.0255 times 1 is 0.0255. Divided by 3 gives me the moles. Divided by 3 equals 0.00, still no significant figures, 850. That's to 3 significant figures. Right, now I've got moles of citric acid and I've got a volume of citric acid. I've got moles and I've got volume, and moles divided by volume is the concentration. But my volume has got to be in dm cubed, and currently it's in 12.13 cm cubed. So the easiest way to do that is just divide that by 1,000. Right, so 12.13 divided by 1,000 equals 0.01213. I'm just going to leave that on there like that. Moles divided by volume gives me concentration. So my moles is 0.000850 divided by my volume 0.01213 equals, gives me a concentration of 0.0701 moles per dm cubed. Right, which I pray to God is the right answer. Check the mark scheme. You'll never see this video, of course, if it's not correct. It is the correct answer. 0.0701 moles per dm cubed is the correct answer. Now the mark scheme says, and this is absurd, if somehow you managed to get that correct answer but you didn't show any of this working out, you would only get 1 mark. So you absolutely have to show you're working out. I advise you to do it in this mole table form with the arrows. People can see what's going on. That was, I'll be honest with you, I've seen easier titration questions on AS level papers.